chapter 14, we're continuing with thermodynamics by talking about heat. So first of all, we're going to start off with a couple of calorimeter problems. We have an aluminum kettle with a mass of 1.5 kilograms containing 1.8 kilograms of water, and we want to heat the kettle plus the water from 20 degrees C to 85 degrees C, and we want to know how much heat must be added in order to raise the temperature by this amount. So we know the amount of heat, Q, is equal to mc delta T, and we need to heat up both the aluminum kettle, which has a mass of 1.5 kilograms, and the water, which has a mass of 1.8 kilograms. So Q total is going to be mass of aluminum, specific heat of aluminum, times the temperature change, 85 minus 20, plus the mass of water times the specific heat of water times the temperature change. So the mass of aluminum is 1.50 kilograms. The mass of water is 1.80 kilograms. We need to look up the specific heat of aluminum. For aluminum, it's 900 joules per kilogram degree C. For water, we know it's 4,186 joules per kilogram degree C. That's 1 calorie per gram per degree C. So now all we have to do is plug in our number. So total heat is mass of aluminum 1.5 times specific heat 900 times 85 minus 20, which is 65, plus the mass of water 1.8 times the specific heat of water 4186 times the temperature change, which is 65, and we get 5.78 times 10 to the 5 joules. Alright, next problem, we start off with, again, metal and water, but this time we have them at different temperatures. We put them together. We want to find out what the final temperature is. Alright, so we have a chunk of copper, which has a mass of 500 grams. We better put that into standard units, 0.500 kilograms. Its initial temperature, well, it's been in boiling water for several minutes, so its initial temperature, and we're going to put a subscript copper on it because it's different for water and for copper, starts off at 100 degrees C. And the specific heat for copper is 390 joules per kilogram Kelvin. And we drop it into water. The mass of the water is, we've got 200 milliliters times 1 gram per milliliter, so that's 200 grams or 0.200 kilograms. The initial temperature of the water is 20 degrees C, and the specific heat for water is 4186, or this problem tells us to use 4190 joules per kilogram Kelvin. So you notice this specific heat is in joules per kilogram Kelvin. That's the same units as joules per kilogram degree C, because again, remember, 1 degree C temperature change is also 1 degree Kelvin temperature change. Alright, so what's going on here? Well, what happens is that the heat lost by the copper has to be equal to the heat gained by the water. Okay, because we said there's no heat lost to the environment. And of course, lost heat is negative, so we're going to have to take the absolute value. So we need to make both sides positive. Alright, so how much heat is lost by the copper? Well, remember, it's mc delta T. So it's the mass of copper times specific heat of copper times delta T. And I need to write my delta T so that I get a positive number. Okay, so what happens? Well, I have a hot piece of copper and cold water. I put them together, and what happens is the water warms up and the copper cools down to the same final temperature, TF. So TF is going to be less than 100. So to make it positive, I'm going to write it like this. So I've got 100 minus my unknown temperature, which I'm trying to solve for. On the other side, I've got the mass of water times the specific heat of water. And now I need to have positive temperature change again. I need to make both sides positive in order for them to be equal. And now the water gains in temperature. So T final is going to be bigger than the initial temperature. So it's going to be like this. All right, so in order to solve for TF, I need to throw in some numbers and do some algebra. Okay, so mass of copper is 0.5 times 390 times 100 minus TF. On the other side, I've got the mass of water, 0.2 times 4190 times TF minus 20. All right, so now let's multiply these numbers through. So half of 390. So I get 195 times 100 minus TF, and on the other side I get 838 times TF minus 20. All right, so now let's multiply through. So I get 195 minus 195 TF is equal to 838 TF minus 167.60. All right, now I want to bring all the terms with TF onto one side and all the numbers on the other side. So I'm going to add this over to that side and add that over to that side. So on this side I get 19,500 plus 16,760, so 36,260 is equal to 838 plus 195 is equal to 1,033 TF. So TF is equal to 36,260 over 1033, 35.1 degrees C. All right, so as we expected, the copper's cooled down from 100 to 35, and the water's warmed up from 20 to 35. So this is one of the standard types of calorimeter problems. The other standard type is to find a mass. So now what I have is I've got 0.2 kilograms of ice at -40, and I mix it with a mass m of water that has an initial temperature of 80 degrees C, and we want to know if the final temperature gets to be 20 degrees C, how much water did you start off with? And they tell us the latent heat of fusion for water and the specific heat for water. So now I've got two complications here. One, I need to find out how much mass of water I have, and the other thing is I need to put in the fact that the ice melts. So if we look at the picture, what we have is the ice starts off at -40 degrees C. We add heat, and it goes up to 0 degrees C. Then we add more heat and melt it. And it's still going to be at 0 degrees C. And then we add more heat, and we get up to its final temperature of 20 degrees C. Okay, so we have to first of all heat the ice from -40 to 0, and then we need to melt the ice, and then we need to heat water up to 20 degrees C. Since we know how much mass of ice that we have, we can figure out how much is involved in each step. So in this step here, it's going to be the mass of ice times the specific heat of ice times the delta T, which is going to be 0 minus -40, final temperature minus initial. Then to melt the ice, we need the mass times the latent heat of the fusion for ice. Then to heat the water from 0 to 20, we're going to have the mass of the water, which is still going to be 0.2 kilograms. We haven't added or removed any molecules, so the mass will be the same, times the specific heat for water, times the temperature difference, final minus initial. Okay, so if I wanted to add up the amount of heat that it takes to warm the ice from -40 to +20, I need to add up these three things. So you can see we're going to need the specific heat of ice, the latent heat of fusion for water, and the specific heat of water. I've got the specific heat of water and the latent heat of fusion for water. I'm going to have to look up the specific heat for ice, and if I look that up, I get specific heat for ice is 2030 joules per kilogram Kelvin. Okay, so the total heat required to warm up the ice is equal to the mass, 0.2, times the specific heat of ice, 2030, times the temperature change, 0 minus negative 40 is plus 40, plus the heat needed to melt the ice, mass times the latent heat of fusion, 334 times 10 to the 3, plus the heat needed to warm the water from 0 to 20. So the mass of water, 0.2 kilograms again, times the specific heat of water, and they tell us to use 4190 times the temperature change, which is 20. So the total amount of heat that was put into the ice is 99,800 joules. Now, if no heat is lost to the surroundings, the amount of heat that's put into the ice must be the amount of heat that's lost by the original amount of water. Okay, so let's write that down. So the heat gained by the ice has to be equal to the heat lost by the original water. Okay, so we know the heat amount is 99,800 joules. The heat lost by the water is the mass of the water times the specific heat of the water times the temperature change of the water. Now the water initially was at 80 and it went to 20. And remember, I'm going to make both sides positive, so I'm going to write it like this. So 80 minus 20, even though that's initial minus final. So remember, I'm going to make this absolute value, so that's the amount of heat lost, not the sign lost. Okay, so I know the specific heat of water, I know the temperature change, I don't know the mass. So all I need to do is say the mass is equal to 99,800 over 80 minus 20, 60 times the specific heat of water. That's 99,800 over 60 times 4190. And so I started off with 0.397 kilograms. So that's 397 grams of water. Alright, now let's do a problem with heat transfer. So there's three methods of heat transfer. Convection, for which we don't have an equation, it's too complicated. Conduction and radiation. So we're going to do one question with conduction and one question with radiation. So our equation for heat loss by conduction is that the rate of heat loss, Q over T, is equal to K, which depends on the material, that's the thermal conductivity, A, the cross-sectional area, times the temperature on the hot side minus the temperature on the cold side over L. Why do we do temperature on hot minus temperature on cold? Because the heat flows from hot to cold, and we want to have our heat flow being a positive number. So heat current is what they're asking for. That's this Q over T, so that's what they're trying to get us to solve. They tell us the area of the wall is 1.40 square meters. They tell us the fiberglass is 4 centimeters thick, so that's our L. And remember, we need to put everything into meters. Our T1 minus T2, hot minus cold, T1 is 175 degrees C, T2 is 35 degrees C. Do I need to do any conversion to Kelvin? No, I don't, because I'm doing temperature difference, and remember, a temperature difference in Kelvin is the same as a temperature difference in Celsius. Then we're told fiberglass has thermal conductivity, that's our K, of 0.040 watts per meter Kelvin. What's the heat current through the insulation? So now it's just a matter of plugging it in. So Q over T, the heat current, is equal to 0.040 watts per meter Kelvin. Let's put in the units so we can see how it works out. A is 1.40 square meters. T1 minus T2, 175 minus 35 degrees C, or equivalently Kelvin. and the length is 4 times 10 to the minus 2 meters. Okay, so plug that in your calculator. I get 196, and what's the units? Well, units should be heat over time, so joules per second or watts. Let's see if that works out. So let's look at my units. I've got a meter, cancels one of the meters there. Then I've got a meter in the denominator, cancels that meter. So those units cancel out. So I've got watts per Kelvin times the temperature. That cancels out. So I'm just left with watts. Okay, so the heat current, or the rate of heat loss, is in watts, 196 watts. All right, last question, radiation question. What's the rate of energy radiation per unit area of a black body at a temperature of 2500 degrees C? All right, so now our equation is Stefan-Boltzmann equation. Delta Q over delta T is equal to E sigma A T to the fourth. Okay, E is the emissivity, and for a black body, the emissivity is equal to 1. On a problem you might be given the emissivity of something, it'll be between 0 and 1. 0 if it's totally reflective, and 1 if it's totally absorbing. Sigma is just a constant. Stefan-Boltzmann constant, 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. A is the area, and T is the temperature in Kelvin. Okay, so temperature in Kelvin, we've got 2500 degrees C plus 273.15, so I get 2773.15 Kelvin. What are they asking us? What's the rate of energy radiation per unit area? So rate of energy radiation is delta Q over delta T per unit area, so they want delta Q over delta T over the area. So that's just going to be E sigma T to the fourth, and we know all these things. E is 1, sigma is 5.67 times 10 to the 8, and the temperature, 2773.15 to the fourth power. And I get 3.18 times 10 to the 6, 3.18 million. What are the units? Well, delta Q over delta T is watts, joules per second, and the area is in meters squared, so this is in watts per square meter. Okay, so there's an awful lot of energy radiating out of that black body.